So if I of t equals the cosine of 2500 t minus 45 degrees, then our amplitude is 1 and our phase shift is negative 45 degrees. So our phasor then is 1 at an angle of negative 45 degrees. Now I'm also going to go ahead and write this in complex form, which means that I'll just think about this thing on the complex plane, right? It's a magnitude of 1 and an angle of negative 45 degrees. So it looks like this, where this is 1. So that means then that our real component is the square root of 2 over 2. And our imaginary component is the square root of 2 over 2, negative. Okay, and that's going to be useful for my approach to this problem in just a moment. So square root of 2 over 2 minus the square root of 2 over 2 j. Okay, now we want to write our components into, convert our components into impedances. So Z of R is simply 10 ohms. And Z of C, remember, uses the formula 1 over J omega C. One thing that I tend to do with these as I'm solving them is I'll just move the J upstairs, because remember, this thing needs to be written into a standard form. We can't have J in the denominator to leave it in standard form. So convince yourself that 1 over J is equal to negative J. Simply like this, 1 over J. If I wanted to put that into a standard form, I'd have to multiply it by J over J. I'd get J over negative 1, or negative J. Okay, so this is negative J times 1 over omega C, which is negative J times 1 over omega, this is omega right here, 2500 times 20 times 10 to the negative 6 for 20 microfarads. And if you work that out, you'll find that this is minus 20J. Okay, so now we have our impedances, and we have our phasor, so we can redraw the circuit in the frequency domain. So I'll redraw it here. This is the square root of 2 over 2 minus the square root of 2 over 2j. This is minus 20j. And this is 10 ohms. Remember that this is also in ohms. So now we have a really simple linear circuit, and we can use any method at all. So just to prove that, it would be really simple to solve this by doing a source transformation. We've got a current source and a resistor, essentially, in parallel. So let's convert them into a voltage source and a resistor in series, and then we can just do voltage division to find this voltage, which is what we're looking for. Okay, V across here. Okay, so to do a source transformation, we are going to multiply this current times this resistance or impedance, and that will give us the voltage source. So let's just redraw the circuit, and then we'll calculate the values. Okay, I'm going to go over and do this in Mathematica. And here is the equation. This is the current, and this is the impedance. Okay, if you're not familiar with some of this stuff in Mathematica, this I stands for the complex number I, and you can get it by typing escape 2 lowercase i's and then escape again. You can also use a capital I, and it works just the same. Okay, and then the / n gives us a numerical value. So when I compute that, I get this for my voltage. Okay, so that's negative 14.14, negative 14.14. So this is negative 14.14 minus 14.14 I, or I'm sorry, J. And then this is still negative 20 J ohms. Okay, so now I have a simple circuit with essentially two resistors that are in series, and I can just use voltage division here. So V equals 14.14, that's negative 14.14 minus 14.14 J volts times 10 over 10 minus 20J. Okay, so I'll come over into Mathematica and just plug that in really quickly. So I'll just take this and copy it. And I'm going to put it in parentheses because I want to multiply this entire expression times 10. This is control / to make a stacked fraction. 10 minus 20 I. Okay, and when I calculate that, I get this value here. So I have V equals minus 2.82. Oops, let me just check that again. I'm sorry, 2.82 minus 8.49. Now, it's important to remember that this is in complex form. Remember how we converted from the time domain to the frequency domain.